Okay. So today we're gonna have two chapters. Okay, but one small chapter, another one quite big. Okay. So we will start with this one. Okay, presentation. Okay, that. Okay, I'll start with this one. Okay, chapter 4 concerning boundary value problem. Okay, so last week, chapter 3 was about initial, right? Initial starting point, initial value problem. So this one is about boundary. So it link. Okay, when from initial, now we're going to learn about boundary. Okay. So of course, you are going to apply some of the methods that we have learned in initial value problem. Okay, there are still people coming in, entering. Okay, so boundary value. So this one is just a small chapter, only one method that I'm going to show. Okay, so boundary value problem. So ODE, remember ODE is ordinary differential equation. Okay, so like a normal, okay, general differential equation, okay, with dy dx or dt dx, etc. Okay, differential equation. So these conditions are used to evaluate the integral that result during the solution of the equation. Okay, so we are going to have a set of ODE, ordinary differential equations, and we are going to solve, okay, by knowing the boundary values, okay, of these differential equations. We are going to learn how to solve. We are going to apply the method to solve this differential equation. Okay, so for example, if we have n order of differential equation, okay, so we need n conditions. Okay, so if all conditions are specified, okay, then we have an initial value problem. Okay, so basically from what we are going to do in boundary value problems, we are going to have a set of equation. The examples that we are going to see, inshallah, later on is a second order differential equation. So basically, for boundary problems, we normally will have a second order or higher second order differential equation. So from this second order differential equation, we are going to separate the equations into the first order. So when we have the first order, then we can apply the initial value problem that we have learned before. Okay, so we will see. Okay, if the conditions are specified and different values of the independent variable, usually at extreme points or boundary of a system, then we have a boundary value problem. Okay, so we other than initial value point, okay, if we are given boundary values, okay, boundary value normally is at the extreme points. Okay, means initial and at the end, or if you have a control volume. So sometimes you are given with the values given at the outer part of the control, at the extreme part or at the external part of the control volume. So that is the boundary values. Okay, so we are given we are facing the boundary value problems. Boundary value problems. Okay. Okay. Okay, so this is an example in a graphic. Okay, before this we have initial conditions for initial value problems, right? Last week, okay, we have seen this. So for example, we have equation, set of equations. So this is a set of ordinary ODE, ordinary differential equation. Last week we seen only we have seen only one set of one equation. Okay, but differential ODE, we can have a set of differential equation. For example, here we have two set of two differential equation. Okay, so we have two, means we have two function, dy, we call it as dy1 and dy2. So if they are functions f1, f2. Okay, so for example, like this graphic given, so we are given with the initial value y1 equals to the initial value of y, y2 initial value of y2 for this function. Okay, so this is a set of ordinary differential equation, ODE. Okay, if we have this, then we can solve this equation for initial value problems. Okay. Now, for boundary values, okay, we need a second order equation, okay, of the differential equation. We need the second order. So this second order is also a function. So for example, a function like this, okay. So we are given with the boundary condition. Boundary condition, for example, first one is at the initial point, okay, and the other one is at the end. Okay, at the extreme point, at the final point. This one is L. For example, we have a distance L from 0 to L. So we are given the value of Y for initial 0 and for the final point, at the final point L. So this is a boundary value problems, okay? So we need a second order equation, second order function. Okay, so general problems, example of physics problems that we need in order to solve, we need boundary value problems or second order is a heat transfer. Okay, so a heat transfer problem is an example of second order boundary value problems that we can use to apply these boundary value methods. Okay, so okay, so basically in this chapter and the next chapter, we will apply the heat transfer problems to solve these boundary value problems. Okay, so here for example we have a rod, macam batang macam tu, ruler batang, a rod. Okay, so with boundary, okay, temperature T1 and T2. Okay, so for the initial point, we note it as x0 and the distance from 0 until L. Okay, so we have boundary condition T1, T2 at the extreme points, and we also have the this is normally the ambient temperature. So this ambient temperature also are boundary values that are given. So this ambient temperature will affect, okay, the temperature of the rod along this distance. Okay, so the rod here will change, will transfer heat. Okay, the process of transferring heat, we call it convection. Okay, convection will occur, convection heat transfer will occur between the rod and the ambient, because the rod has a different temperature than the ambient. Okay, so when we have two fluid or two solid and fluid with different temperature, then normally a heat transfer process, which is convection, will occur. Okay, so this one, the heat transfer convection, okay, convection by heat transfer by convection will occur throughout the rod. Okay, so the rod will exchange heat with the ambient. So this is a normal general problem for heat transfer. Okay, some of you that have done in the second group of for aerospace lab 2, the second group, okay, that have done experiment with me for thermofluid before MCO. So you have seen the lab 3, lab number 3, the heat transfer problem concerning rod, right? Okay, so you must be you must understand this clearer. Okay, okay. So for example here, okay, so we have this heat transfer equation. This is a normal equation for heat transfer, so it is in a second order. Okay, so the function is T, temperature. So the second order differential equation, the second order differential equation of temperature along the distance x. Okay, so H prime is the is in the waiting list. Okay. Tak dengar tadi ya. Okay, so H prime is the heat transfer coefficient, okay, in meter per second, meter square per second, and TA is the ambient temperature, and L is the distance of the rod, okay, 10 meter. Ramai lagi masuk. Okay. Okay, so this is a general heat transfer equation. Okay, so we have the boundary conditions given. So at distance x0 at the initial point, it's also called T1, is the temperature is 40 degree. So we assume this one is 40 degrees. Okay, and at the end, T2 or at the point at the distance L, the boundary condition here is 400. Okay, 200, sorry. So by solving this analytically, means by method of calculation that you have learned before in engineering maths, analytically, we can solve this second order differential equation, and we have this set of analytic solution. Okay, later on I will show you example of another set of equation. Okay, just to explain first. Okay, so this is the analytic solution. If you solve it by calculation manually, this heat transfer coefficient, you will get this analytical solution. Okay, with constant 20 degree ambient. This is constant value. Okay, so what I'm going to introduce in this chapter, boundary value problems, is a method which is called the shooting method. So by the name, by its name, shooting means that you just like, kalau bahasa Melayu in Malay language, jawab exam tu kata tembak je kan, tembak je. So something like that lah, shooting method. So we have to assume some values, okay? We have to make assumption, shooting method, tembak je, okay? So converts the boundary value problem to initial value problem. So what this shooting method, how are you going to apply this shooting method, is that we have to first convert, like I've said just now in the beginning, we have to first convert the boundary value problems, means that we have to convert this second order equation into initial value problem, means into first order equation. So means that if we have second order equation, we try to convert the second order into two first order differential equation like this. Okay, we separate into we change it into first order, but it becomes two set of equations since it was second order. Okay, so we will now face with the initial value problems. Okay, like last week. Okay, we have learned. Okay, so a trial and error. So trial and error, we try and errors. That's why it is called shooting method. Okay, try and error. Approach is then implemented to solve the initial value approach. Okay, so we solve it like a initial value approach. It's just that we have to make some assumption. Okay, we have to play around. Okay. Okay. So for example here, the second order equation just now, the heat transfer equation can be expressed as two first order ODEs. So we express like this. Okay, dt over ds, we call up a new parameter z. Okay, we just note it as z. So dt ds is equal to z, and this function z is equals to the h prime t minus ta. So we try to separate this. Okay, this set of second order differential equation, we separate it into two first order equation. And with an initial value guess. So this is not given. Since z is a value, assumption value that we assume, so we have to assume also its initial point, initial value. Okay, so we assume here, let's say z0 at point 0 is 10. Okay, we assume. Okay. The solution is then obtained by integrating the two first order ODEs simultaneously. Okay, so we have to integrate this and integrate this. Okay, so we can apply the initial value method that we have learned last week, which is the Euler method or the Runge-Kutta method. Okay, to solve this these two set of equation. So for example, I gave first the example, later on we will do exercise together. So example, by using a fourth order of Runge-Kutta method with a step size of 2, okay, we use h equals to 2, step size 2, because we have 0 until 10, so means that we have T1 until T5. Yeah, T0, T1, T2, T9, and T5, because there is the distance is 10 centimeter, right? So we divide by 2, so 5. Okay, so T10, by using the Runge-Kutta method, we have T10 168.3797 Kelvin, degree, I think, degree Celsius. Okay, so what we see here, okay, we realize that this value differs from the T10 boundary value given here. Okay, we have the boundary condition given here, T2 or TL 200. Okay, wait baby saya nangis sekejap Okay, sorry Okay. Apa tadi? Okay, so okay, when we apply the Runge-Kutta method, we calculate using the Runge-Kutta method for further. Okay, so we have T10 at the extreme point, the final point 168. However, if we look back at the initial problems, okay, we have this boundary condition TL, or at the 10 meter, is actually 200. Okay, 200 degrees. Okay, so therefore a new guess is made. So we have to shoot again. Okay, we have to try again. Okay, because the solution differs. Okay, differs quite big. So depends on the percentage of error that we set. Okay, so now we try again. Okay, for example, we try again, make a new guess. So this time around, we make a new guess, Z0 equals to 20. Okay, the first round was Z0 equals to 10. This is just assumption. So now we assume Z0 equals to 20. So, and then we perform again. Okay, the computation perform again. And we perform again the fourth order Runge-Kutta method. And then we get T10 285. Now it become higher. Okay, higher than the initial the boundary condition given. Okay, 285. Okay, so since the two sets of options, Z1, Z2, the first one, which is 10, Z0 10 and Z0 20, are linearly related. We assume that it is linearly related. A linear interpolation formula is used to compute the value of Z0 as linear to determine the correct solution. So means that we assume that this Z equation is a linear equation. So by interpolation, okay, we have these 2 points, right? We have these two solutions, 168 and 285. So we did an interpolation, okay, to get the midpoint. Okay, we're going to assume which is the correct point. Okay, so we have this Z0. By doing the interpolation, we have Z0 is actually 12.69 or 12.7. So means that we are going to search for the the value of Z at the initial point, okay, at the zero. So we have 12.69. Okay, so it must be in between because our first assumption was 10, second assumption was 20. So we try to search this value of Z in between. Okay, so we assume 12.69 means that we assume that if Z0 equals to 12.69, then we're going to get T10 equals to 200. Okay, this is what it means. Okay, after doing the interpolation, okay, we achieve a Z0 at 12.69. What does it mean? It means that if Z0 is equals to 12.69, we are going to get T10 equals to approaching 200. Okay, to determine the correct solution, which is 200. Okay. So this is graphically, if we explain this graphically, so means that first time, the first one, okay, 168, right? Okay, so example is like this. First guess of Z0, we achieve T168, but the initial solution, the correct solution is 200. So another second attempt, okay, so we get 285, right? 285, which is 285, which is higher than the correct the exact solution. So we did the interpolation and find the Z0 in between. So we assume that we can approach the exact solution to 100. So the Z0 is 12.69. So that's it. Okay. So that is the shooting method. Okay. Okay. So now, okay, I'm going to show one example, which is more likely like this example, this just now. Okay. So now we have this heat transfer equation dt second order. So like this one, is dx square minus 0.15 T equals to 0. Okay. So now we're going to try the shooting method. Okay. dt square over dx square minus 0.15 T equals to 0. So this is our equation, okay, example that we're going to do. And we have T0 equals to 240 and T10 equals to 150. So this times means that the road, okay, the heat transfer, the road will be cool, okay. Just now will be heated from 40 to 200, but now it is cool from 240 to 150. Means cooling process. Okay, this is cooling process. Okay, so we have this example, set of equation dt square over dx square minus 0.15 T temperature equals to 0. Set of boundary conditions T0, T at 0, 240, T at 10, 150. Okay. Try to solve this analytically first. We want to see the analytical solution. Okay, like normally you solve the a differential equation. What do we have? Okay, in terms of equation, for example, like this one, we have like this 0.1x. So we have to assume that t is an exponential function. Okay, try to solve this analytic first, and then we do the shooting method. Okay, salin na Okay, supposedly, if we solve this analytically, we suppose that t is a function exponential lambda x. T is an exponential equation lambda x. Okay, lambda is a constant value. Okay, so if we have, so replace this exponential lambda x in the second order equation just now.
Doctor.
Yeah.
Your camera is too below. Okay, thank you, doctor.
Okay, sorry. So t equals to exponential lambda x, huh? So you will have the solution, something like this. So you have tx k1 constant exponential. Okay, so lambda, I have calculated the lambda is actually square root of 0.15. 0.15. Okay, x plus k2, another constant, exponential negative, so positive negative, 0.15x. Okay. So you have a solution like this. So you have to find K1, K2. How to find K1, K2? With the boundary condition given. Okay, we know that at T0 is 240, T10 150. So by substituting the boundary conditions, so we can calculate K1, K2. Okay, I give 1 minute because I won't give too much time. I won't concentrate a lot on analytic solution, because we are going to focus more on the shooting method. Okay, just this analytic solution just to compare later on. Okay, so that you can compare your solution by from analytical and the shooting method. Okay. Okay, you can continue the calculation of K. Okay, next the shooting method. Okay, this is more important. Okay, shooting method. So, so we divide, we separate, not divide, the equation, the heat transfer equation into two first order equation. So dTds equals to Z, and then another one, dz dx equals to 0.15 t. Okay? So we separate it, dTds equals to Z and dz dx 0.15 t. We separate into two different first order equation. And we will apply the initial value method. Okay, so here, just now in the slides, I've shown the example that use Range-Kutta method. Okay, so for this exercise, I choose to solve it with Euler method because it's more simple, it's more faster. Okay, but we can also use a Range-Kutta method, either one. Okay. Okay, so so this means that if we have a road, a distance 0, so this is x0 and this is xl, which is 10 meter. So the initial value t is 240, 240 and final point is 150. Okay, so x0 240 degree, x10 150. Okay. Okay, so if we are going to apply the Euler method or even Ranskota method, we have to make some assumption. Okay, the first assumption that we have to make is that because we don't know the values of dt dx. Yes, dt dx is equal to z, but what is the value of z? So we don't know that. So we have to assume. Okay. So here I'm going to assume that tx dt dx or t prime x at the initial point. Okay. T prime means dt dx, but at the initial point t0 0 equals to 200. Just assumption, huh? I just try to take a value which is in this range. Okay. Yeah, because if you remember the initial values problem last week, we need the values of the differential equation at the initial point. We need y prime 0, right? So we have to guess this value. Okay. Okay, now we are going to write the equation. Okay, macam nak tulis? Ingat. 10.15. Okay. Okay. Seperti tak kata tadi. Okay. So I'm going to write like this. Seperti tak padam tadi. Silap. Okay. D dx z. Right? Okay. So I'm going to call it a function f1. Okay. So it is a function. The differential equation is a function f1, which is depends on x, t, and z. Okay? And dz, dx just now, 0.15 t, 0.15 t. We are going to call it as function f2. So we have two functions, which is also depends on s, t, z. Okay. Okay. Okay, so we have f1, f2 function. So now we are going to start to apply the Euler method at point 1. Okay. Okay. And the step size, I just choose 5 because nak cepat calculate. Okay. Just example so that we just divide T1, T2. Okay. Okay. So 5. Okay. Now T1. Okay. T1 is equal to T0 plus F1. So F1 at 0 depends on S0, T0, Z0 times H. This is the Euler equation last week. Okay? This is Euler equation last week. Y1, Y0 plus function of Y multiply the step size. So this is from last week. It's just that here is temperature T. Last week we used Y. Okay. So the same thing for Z. Same thing for Z. So Z1, Z equals to Z0 plus F2 X0, T0, Z0 times H, the step size. Okay, this is from last week equation. Euler method, tengok balik. Okay, so Okay. Okay. Okay, so T1 again, T0 is given in the boundary values 240. Okay, T0 is given 240. Okay, so this function T prime 0 just now, F1 is T prime 0. So we assume just now 200, right? Okay, so 200, this value is assumed. So times the step size 5 that we have chosen. Okay, so we have here 1240 for T1. Z1, Z0 is what? Z0 just now is the T prime. Okay, so Z0, T prime 0, which is 200, just 200. Okay, that we have assumed. Okay, 200 Z0 plus okay, so the equation F2 is 0.15 T just now. So 0.15 lambda 0.15 times T 240, T0 240 times H, step size. Okay, F2, if you remember, F2 is 0.15 T. So 0.15 T, T0, 240. So times 5, which is equals to 380. Okay? So we have the values of T1, Z1. Faham tak ni? Okay. Kita tengok balik. Okay, this one. Okay. Okay, I repeat again. Okay, we separate. Okay, by using by applying shooting method, we separate the second order equation or heat transfer just now into two first order differential equation. So in the example given that we're going, we are doing right now. Okay, in the example given, so we separate into dt dx equals to z, a function z, a new function z. And another one, dz dx is equals to 0.15 t. Okay, in our example, 0.15 t. Okay, and then we have to make a guess. Okay, for z, which is z is actually t prime. Okay, so the same lah. Okay, so t prime at 0. T prime 0, here in our problem here, we assume T prime 0 is 200. I assume lah 200, okay? Okay, T prime 0, 200, okay? So this T prime 0 is also equals to Z. Okay, that's why Z0 here is 200, okay? What else? Okay, so we apply the after separating the boundary problem into initial value problem to first order problem. So we choose to apply the Euler method, not Runge-Kutta. You can also use Runge-Kutta, but here we use the Euler method. So last week we have learned Euler method. The equation it is not a new equation. It just comes from the different definition of derivative equation. So we have this equation, T1 equals to T0 plus F1, the function F1 is the dt dx times the step size. Okay, if you remember, something like this, yi plus 1 equals to yi SI plus dy dx times the step size, which is here, if you want to write in terms of x, is si plus 1 minus xi. So this is actually this equation. This comes from the derivative equation. So it is nothing new. Okay. So Euler method actually it applies the derivative equation definition, derivative definition. Okay. So we just apply here. So for example, this is t1 at I0, t0. So dy dx is the function f1. Okay, which is this one, dt dx, and x, the step size, si plus 1 minus si is the step size. Okay, so it's this equation, derivative equation, nothing new, huh? Okay, so we do both of these equation, Euler equation method for t and z, because now we have two first order ODE. Last week we only have one. This time we have two, so we have to do twice. Okay, for T1 and Z1. So the same definition for Z. Z1 equals to Z0 plus F2. F2 is the derivative equation of dz dx. F2 is dz dx. But here in our example, dz dx is 0.15 t. Okay, which is we call it as F2, function 2 times h, the same. Okay, time h. Okay, not to be confused, this h is not the same as h ni, yeah. H, this h is the heat transfer coefficient if it's given. This one h is the step size. Okay, so we substitute the values that we have, okay, to calculate T1 and Z1. So T0 is 240, the boundary condition given. F1 dt, which is dt dx, 200, which is assumed by us, and the step size also chosen by us. Okay, so you can choose 5, you can choose 2, as long as it is in between from 0 to 10. Okay, because the distance is 10. So I choose 5 because I want to calculate just quickly, okay, faster. But it is better if you choose a smaller step size. Okay, so 200 5 so equals to 1240, and Z1, so Z0 is actually T again, T prime 0. So we use the same value that we have assumed, 200 plus F2 is dz dx. Okay, dz dx in our equation is 0.15 t. So that's why 0.15 t, T0 is the boundary condition, 240 times 5h, the step size. So we get 380. Okay, so we have T1, Z1, and then we calculate again for T2, Z2. T2, Z2. Okay. So the same thing, T2, T1 plus F1, but this time depends on S1, T1, Z1 times H, and Z2 equals to Z1 plus F2 H. Okay? Okay, tapi yang ni start calculate habis. I didn't calculate until finish. Just put in the values. Okay, 1240 plus 380 times 5. 380 because of this. This one 380 again. Plus 0.15 1240 times 1240 times 5. Okay, I didn't finish calculate it. Okay, just to show you, okay, the methods. So once you have the T2Z2, then you compare the values of T2 with the boundary condition given. The boundary condition given in the questions, T2 or T10, because 10 meter is 150. So I think you're going to get something bigger, 1,000 something. Okay, so it is far away from the exact solution, which is 150. Okay, so we have to make a new guess. Okay, So maybe the second round, second round calculation, we have to assume a t prime 0. Just now we assume 200, right? So we have to assume something smaller so that we can get a smaller solution. And then from both of these solution, then we do interpolation, and we will approach the exact solution t. Faham tak? Okay. I don't have a calculator here, but I think it will be something bigger. For example, okay. For example, we get 200. Example, just example. Please calculate it carefully, okay? Correctly. So 2,000. For example, if we get T2 here 2,000, okay. Then we compare with the boundary condition given, which is 150, which is we are far from the exact solution. So we have to do a second round of calculation, all of this, okay? Second round, so logically we will assume now this time for the second round, we will assume a value which is smaller because we want to try to get a smaller solution to approach the exact solution 150. So maybe this time around, the second time, for example, just now, first round, we assume t prime 0, 200, right? Okay, so second round, maybe we choose t prime 0, something 100 Kelvin, 100 degree. Okay, and then we do again the Euler method. Okay, and then we do the interpolation of the values. Okay, like this one, interpolation to find the point Z0 where for the correct, to determine the correct solution. Okay, so that is shooting method. Okay. Okay,
okay, doctor.
Okay, so you have to try, okay? Okay, okay, so finish for this chapter, boundary value problems. But we haven't finished the class yet. We have another chapter, but I'm going to suggest 5 minutes break, okay? 5 minutes break before we continue the next chapter. Okay, in the meantime, you can take a break, or you can try to continue the calculation just now. Okay, we take a break 5 minutes. Okay.
Okay, doctor.